Okay, so I think I'm going to get started. It's 1:01 here. My name is Caroline Amyot. I am a senior project engineer with the City of Waterloo, and I will be your moderator today. I am on the Education Outreach Committee at CUIIC. And today I will be moderating Dr. Mark Knight, who will be speaking on common pipe and liner live load specification misunderstandings. This was when we were planning the webinar series. We think this is a very exciting topic, and we think there's lots more to go. So there's a lot to cram in this next 20 minutes from Dr. Mark Knight. So think of this as a bit of a teaser or like a movie trailer. So we're hoping to build maybe even a full day workshop on this. Just before I move on to talk a little bit more about the webinars, if you have questions during Mark's presentation today, if you could just at the bottom there, hopefully you all are used to Zoom, there's a chat and I see some of you already used it. Please use the Q&A and I will be reading those and we'll address those at the end. So rather than raising your hand or using the chat, please try to use the Q&A button at the bottom. Okay, so just a quick little introduction into the CUIIC webinar series. Mark, if you just want to, there we go, CUIIC webinars. As I said, this is a new education series that we've organized for fall 2022. It's bi-weekly live webinar series. The first one was last week, and it will be running through to December 8th, and then we're planning again more webinars for 2023. You can see all the details on the www.cuiic.ca for the full schedule. Lots of good stuff there. What is CUIIC? CUIIC is a cross-Canada hub for research and education in underground infrastructure. It's located at the University of Alberta. CUIIC is a membership-based organization that involves stakeholders, including municipalities, which is myself, contractors, owners, and others to identify pressing issues facing the underground sector. CUIIC stakeholders represent all underground infrastructure domains, including water, wastewater, transportation, gas distribution, energy, power, and telecommunications. I think the idea with CUIIC is to bring these sectors together because we all face similar challenges when we're dealing with any kind of construction in the underground, so we can learn from each other and learn to work better, because we often have to also cross paths sometimes. So that's part of the idea of CUIIC, is bringing everyone together to learn from one another. So it is membership based and it's open to, like I said, all those sectors we said: manufacturers, suppliers, contractors, consultants, utilities, municipality, and nonprofit agencies. You could also become an official research partner with the University of Alberta. That was the other idea of having this based out of the university, is that we could partnership and use the university to build on research that the industry sees as being required. There's also, we're building CUIIC Connect groups and forums for online discussions. And again, the intent here is across Canada and across all these forums. So it's very exciting. And again, on the website, there's more about the membership if you're interested. Okay, so now to the webinar, why we're all here. So today's webinar on common pipe and liner live load specification misunderstanding will be presented by Dr. Mark Knight, professor from the University of Waterloo. He is an industry leader in the area of municipal underground pipeline design and construction using trenchless construction methods, and he is the past executive director for the Center for Advancement in Trenchless Technologies, and he was my supervisor when I did my master's research at the University of Waterloo. Through his consultancy firm, he has developed industry-leading design tools. He's been retained to complete complex designs, which I've also worked with him on some projects, and as a litigation expert, which thankfully I have not had to contact Mark. Knock on wood, and I don't need to for that. So with that, I'll give it away. I'll hand it off to Mark, and he can let us know all about common pipe and liner live load specifications.
Thank you, Caroline. Can you see my mouse if I move my mouse, Caroline?
I can see it.
Perfect. So this webinar, First, before I start, I want to thank Ali and the group at CUIIC for allowing me to do this presentation and to be involved in CUIIC. It's a really exciting center and opportunity, and it's just awesome to see it start off and to flourish. So what I'm going to try to do is go through some information and assumptions on live loads. This came from work that I've been doing as part of the design and building calculators for CIPP, and then dealing with consultants and owners, and some of the misconceptions and the importance of making sure that we specify these things right. And how it does impact cost and liner thicknesses. There's a variety of different live loads that can be applied at the surface. And I know in University of Waterloo, in our first geotech course, we cover point loads and line loads and foundation loads from square, rectangular, and footings. So those loads, if they're applied, will have this type of distribution with respect to depth. And it will be very high at the surface. And theoretically, it will go off to infinity at the surface. So underneath the application of that load, it will be like this. And if we look at sections away from that live load, we'll have the highest peak in the middle, and then it will start to decrease. So with depth. As we go down with depth, the magnitude of the stress that will be applied will decrease, but the footprint will increase. And if we integrate this area underneath this curve, we have to come back to the surface load that's applied. So it gets smaller, but it gets wider and goes out farther with respect to depth at depth. Some of the design assumptions that we have to understand in order to be able to calculate these live loads. So back in undergrad, we learned that soil is non-linear and not elastic. However, we're going to assume in order to be able to calculate these that the soil is homogeneous, isotropic, and linear elastic. That's not true. So we basically are assuming that all the soil is the same with respect to depth. And it basically is a rubber, block of rubber, a material with all the same material properties. And if I squeeze it down in this direction, it will move out some direction in the horizontal, and that's the Poisson ratio. So we're going to have to assume a Poisson's ratio for the material. So if we have layered type deposits, or if we have a stiff soil over a softer soil with respect to depths, we're going to overestimate the amount of live load with respect to depth. So these are assumptions that are always done in this side, and they're on the conservative side. We can also approximate the loads with respect to depth and the foundations, and we have what's called the Boston rule for foundation design, where this stress distribution is going to go off at 2 vertical to 1 horizontal, and we can calculate the stress with respect to depth. And in that case, we're going to assume that it's linear and constant across this plane. In real life, it's that bubble that I kind of showed you with higher underneath the middle of the foundation and start to decrease as we get out around that foundation. And we can use this approximation method in order to be able to calculate the stress with depth. Nothing new if you've taken the soil course. What we don't teach in undergrad and in many courses is how do we treat live loads from trucks and railway crossings. So we have to be able to go to the literature and look at those ones. So I want to look at where they come from. Because these are the common ones that are being specified for the design of pipes underneath roadways and liners with respect to depth. So we go for truck loading, we go to AASHTO, American Association of State Highway Transportation Officials, and they go back to the 1930s, and they developed a design truck. So it's not a real truck, it's a design truck with different weights and different axle weights. They started with an H15, and then they went to an HS20, which is this truck with 3-wheel axles. And now they went up and kept on increasing the axle weights of these trucks to get an HS 30, which is I believe, a 30,000 pound axle truck. Then we now move to an HL 93 truck distribution. So these trucks have a certain footprint, and we take the weight of that truck and distribute it according to different axle weights. For 40% of the axle or the total weight is on this axle, another 40% on this one, and then we just try, and then we do some calculations in order to be able to do that. If you go back in the literature, there's a variety of different tables that are published in different manuals. Plastic Pipe Institute has a table for flexible surface. Manual AWWA M55 has a table of values and for flexible. The Plastic Pipe Institute, so if you have a rigid top surface, that will spread the load and make it smaller with respect to depth. So then they have a bunch of table values. And then if you do some calculations and you use the calculation methodology, you can do an HS25 truck and a variety of different tables. And if you take those tables and you plot them, so I've got ground depth here on this bottom on the x-axis, and the live load pressure on this axis. So as we go down, that load should decrease. And we plot these, you'll start to see that there's a huge variation in these values. Even though they're specifying an HS20 truck or HS25 truck or HS30, and you go to these tables, you'll get a bunch of different values. And which one's the right one? But they all follow the AASHTO supposedly method. And if you try to do calculations to validate these tables and these table values, you'll find that there's quite a spread, and it's very difficult to be able to do those. So instead of necessarily specifying a methodology, what you may want to be able to do is specify a table of values so that everybody's going to be using the same values for the same specification. So again, if you look at PPI and M55, you'll get completely different numbers. So what do we start to see from these different types of truckloads? Once you get down to 3 meters, you're at 10 kPa or less. So at 3 meters, they basically go to 0. If you're within a meter of the surface, you start to see that there's quite a variation. So I'm here, I'm somewhere around maybe 17, 18 MPa at the bottom. If I use this one, I'm at 50, 5 times more, or close to 4 to 5 times more. If I go up to below 1 meter surface, and I go say to somewhere around 0.6 meters, these things are going to go from close to 40 all the way up to 120 kPa. So huge variation, again, possibly for specifying the same methodology. So if this was is an HS20 truck here on the bottom, and these are the other HS20, I'm going from 40 to 60 kPa. That 20 kPa will make a huge difference in my liner thickness, which I'll show you in a little bit. We can also follow design methodology to be able to do that. Besides the AASHTO truck in Canada, we often specify the CSA trucks. There's basically it's a CL truck with a weight, which is it's the axle truckload, and you got a CL 625, you got a CL 800, you got a CL 900 truck with a weight distribution, and everybody wants to make these bigger trucks. Now you got to remember the design trucks for the AASHTO and the CSA are really designed for designing the bridge structure and the bridge deck for bridges. They were never really intended for distribution of loads on pipes at depth. But again, we can use those, and we can take those weights and bring them back and do the calculations with respect to doing that. So how do we do that? Well, we take the tire load or the axle load that's put on these tires, and we have a distribution for those for that stress at depth, and then we can calculate the area that's being applied to. So and we can do that calculation. So again, different methodologies from different standards have different slopes that distribution, kind of like the Boston rule goes off, and you'll start to see that this tire load and this tire load will stress distribution will overlap at around 0.6 meters if we used a one-to-one relationship. I think CSA uses a 2-to-1 distribution, and different tire trucks. So then the different axles. So we can calculate the stress with respect to depth. So that's how the calculations are done. And if we get to do a course, we'll go through and develop these things. So a truck has multiple axles. So this is axle number 2, and this is axle number 3 for an AASHTO or CL truck, which are relatively closely the same. This stress distribution will start to overlap with this stress distribution, and this is the most critical and will give you the highest stress. So now we have to take the influence of 2 axles together with respect to depth. Anything above 0.6, we're going to use the full stress distribution of the load at the surface. So from 0 to about 0.6, or where that stress starts to overlap, that's where we kind of go into this case. So what's the impact? Well, if I use a live load of 10 kPa for a 675 millimeter pipe, gravity pipe at 3% ovality, and if it's basically a meter below the ground surface, I need a liner thickness of 7.8 millimeters, assuming everything else is constant. If I just change that live load to 100 kPa by because I know at 1 meter I've got a spread of somewhere 10 to 120 kPa, all of a sudden now I need a liner thickness of 14.8 millimeters. So I need twice as thick liner for this live load when I'm around a meter. So it's really a designer's choice of where you get. Now you say, from an owner's perspective, well, the thicker the liner, the better. Well, you may be paying for a much more expensive liner. The thicker the liner, the more difficult it is to install, the much higher cost that you're going to have. And then how do you make sure that you can compare? And I can argue, depending if you just say you will specify an HS20 truck, I could get a liner design submittal that's 7.8 that's going to use a table value for an HS20 truck. I could get another submission that's going to say it's going to have to be 14.8. How do you validate, and how do you verify, and how do you make sure you got comparable designs? And I could argue that the 7.8 meets your design specification. And so that's why I say make sure that you specify a table value than necessarily a methodology. So as I said, these were developed for bridges and not underground pipes. Trucks over the years keep on getting heavier, so everybody wants to specify a heavier truck. I've seen transport trucks like an HL30 massive transport truck that can only go on a highway being applied for a small trail where that truck can never go through there. So again, make sure that the truck that you're going to be applying is going to be representative of something that could possibly be on that load, and just don't pick the biggest and heaviest, because again, it's going to have a huge impact on your liner design and the calculation, and makes it much more difficult to be able to do. As I say, specify a live load table. I know that if anybody's using Ian Doherty's calculator, if you try to put anything less than 0.6 meters or around a meter, it won't allow you to do any calculations. And he will use typically specify the M28, M55, or whatever table of values that he uses in his calculator for that one. For shallow depths less than 2 meters, make sure you understand what the impact and the values of that live load is being, because it has a huge impact on the cost of the liner. Below 3 meters depth, it's really live loads have no impact from truckloads. So just be cautious when you're less than a meter. And if you're over 3 meters, then who cares about live loads? It doesn't really have an impact. Now I want to go to railway live loads, because this is another area that for trains and LRTs and other projects that people will also specify a train live load. This comes from back in the early 1900s, when Theodore Cooper was developing some calculations, and he came up with a design train, Cooper E10 system on that one, which was a certain locomotive pulling an infinite number of cars. Over the years, these railway trains have gotten bigger, and now we're up to almost E90. None of these design trains represent anything that's in service today or have been in service, but their calculation methodology. So there's the Cooper live load wheel configuration that's used in order to be able to come up with some published tables. I don't know of anybody that actually uses this distribution like a truck and be able to calculate the stress with respect to depth. Again, the 80 represents the axle weights of the locomotive on that one. And so E60 is basically the ratio of 60 over 80. So if you've got an E80 table, you can calculate the live loads for E60 by using the ratio of 60 over 80. If I've got an E90 live load specified, I can do the ratio of 90 to and multiply by these the table values by this factor 90 over 80. So, and if an E100 would be 100 over 80. So we can easily convert. We look at live load stress with respect to depth, as we have here. We start to see that these can be fairly significant, and we don't get down to 10 kPa until we get down 25 feet or 7 meters. So railway live loads will go down to a much deeper depth, and they'll have an impact. So if we look at live loads from a live load from an LRT type train with 80 kilonewtons per meter, we will get this distribution, and you'll start to see that somewhere around 7 or 8 meters, they become negligible. So if we're down relatively deep, these railway loads, but at the surface and 1 meter, they can be very significant. We can go up to 160 kPa. So again, make sure that, and these ones are much bigger than the truckloads that we saw earlier than we saw before. So again, make sure that we specify the correct train and the correct table. Again, they have a huge impact on liner thickness and therefore your project cost and constructability. Train and truckloads continue to increase. Make sure you specify something that's reasonable for the site. And just have to remember that loads are worst case values. Typically whatever will be in the field will be much less than what we predict, because the existing hose pipe will continue to arch, and if it's there, we'll shed that load the deeper we get. We have other arching factors that we don't take into account. So again, these are extremely conservative values, and be cautious when you've got a pipe that's somewhere, you know, 1 meter or 1.5 or less than 2 meters depth. Then that you're going to apply something that's reasonable and rational. So that was a relatively quick overview. As Caroline mentioned, I would like to put on a workshop where we can go through the calculation and show how to do these calculations for the variety of different checks. So you can build your own spreadsheet to be able to do these calculations. I have my own that I've built, so I can incorporate almost any load. That's how I did create these plots. It was a great exercise to be able to do that, and then make sure if you had a shallow application that you're very cautious on how you're picking those values. So is there any? I'll end there and take any questions, and if we go past 1:30, I'm willing to stay on and try to answer any questions that anybody has.
Okay, thanks, Mark. We have 2 questions so far. Can you see the question and answer? I can just read it so everyone can hear. The first one comes from Tamer. How are these live load distributions compare to field measurements, if any, or 3D finite element analysis results?
Good question.
Good question.
You gotta have to go back to the assumptions that I mentioned at the beginning. So all these things assume that the soil is linear, elastic, and is all the same material with respect to depth. There are, even in foundation design, we can do, so they'll be probably much higher than what we're estimating in these values. We're very conservative, so they would be much higher than we would actually expect if we did field measurements. I know that we measured live or surface loads and the stuff as part of Dr. Bayet's research at the University of Waterloo with load cells. Again, I would expect them to be, we're going to be very conservative in the design. How well do they match with 3D element modeling? Well, it depends on how good our modeling is. And we can now represent those values, but I don't know of anybody that really does finite element modeling to estimate these live loads, because no one wants probably to pay for it. And they're going to use these conservative designs. Methodology, because that's what they specify. You got to remember that we want to make sure that all bidders, there may be multiple bidders that are putting in designs. The main thing we want to be able to do is make sure that we, as an engineer, if you're the engineer of record in the project, is make sure that you can compare apples to apple comparisons for the designs. And you don't want different designers using different values. And that's why I say specify a table. Otherwise, they may be able to come up with a thinner design that may be not what you really want because of the way that you specified your contracts. So I didn't directly answer your question, but hopefully I did answer it. Does the soil pipe have an impact on the distribution on the live load? It does. In the live load calculations, we assume a Poisson's ratio. And the different soils will have different types of Poisson's ratio. We can use different distributions for foundation design with different soils. If we've got a stiff soil, that will dissipate that live load much faster, and they'll be much lower. But again, we don't get into that complexity for most of our pipe designs in that application itself. And it's the other part of the question is it explained in the standards I introduced? No, they don't take into account multi-layered soil distributions. Again, we make some very simplifying assumptions of that linear elastic soil is not linear elastic and as a material. So again, on that side. Can I please provide an example of a live load for underground pipes and how to develop this table? Well, the main live loads that are specified for pipe design and liner live loads are the different truck load distribution. So most engineers will specify a certain truck. So an HS 30 truck or an HL 93 AASHTO truck. That's as far as they go in the specification. Or they'll specify a CL 625, which is and a CSA standard. So then you would have to either go to a table that has a CSL 625 truck and get that table of values, or you have to be able to do the calculations where you take the stress at the surface and apply it and do the distribution with respect to depth, which is a bit of an undertaking, but it's a good undertaking to be able to do. And if we do that workshop, I'll go through all that calculation methodology as part of that course. So I hope I answered that question. In your experience, how would the courts view the wide distribution of failure loads or loads if a failure happened? The courts will typically go with best practice. I've been involved in several liner designs that have failed, and most of them are relatively deep. So the ones that I've been involved in, that hasn't been the case where the live load has caused the failure of the pipe. So again, if you're specifying if the failure happened and you had a big transport truck and you used and specified the wrong one, and that was part of the root cause, then that might be an important part. I think the thing to remember is we'll typically design with a much higher live load than will ever be in the existing ground condition. You got to remember that if you're putting a liner in an existing pipe that's standing up, that has had those live loads on top of it, and you're going to put a liner on the inside of it, and the pipe is in good condition, that liner will not see any live load because the existing hose pipe will carry all that live load. It's not until the existing pipe gets really fractured or cracked or something. So again, our design is overly conservative already. That's why in part specifying a really high live load that's overkill is making you pay a lot more for a liner system that you're not really using, and you're wasting spending extra money that you could use for another project in part of my opinion. So I hope I answered that question.
You're also reducing the capacity of your pipe, maybe unnecessarily.
Well, yeah, exactly. So the more you do that, but the nice thing about cured in place liners is they've got a much higher C factor than the original pipe. So even though we are losing capacity, our cross-sectional area, we typically gain capacity unless we're in a really small diameter pipe, maybe less than, say, a 4-inch, where that may not be. But yeah, so why take away extra capacity when you don't need to, by putting in something extra thick or twice as thick as than what's needed. A major challenge in the practice is when you are crossing railways, right-of-ways, for example. The owner always wants to send you using the super conservative live load impact. They are not accommodating, and they don't change their minds. Do you have any advice for this? Yeah, I mean, I have been involved in railway crossings and LRT projects where we have worked with the railway liner owners to demonstrate the impact of the cost of the liner. One of the challenges that you may have is they're not the ones that are necessarily paying for the liner. So if the railway wants always something that's going to be super conservative, and they're not the one that's paying the bill, they don't really care if you put in hey, let's put in a 14 or 15 millimeter thick liner versus the 7. However, so that's a little bit more difficult argument to be able to get them to change their mind if they're not paying for it. If they are paying for it, by showing them how the calculations are impacting from the design point of view, and if I'm going to be if the contractor has to be ultimately conservative, they'll typically design using a Cooper E80 load, and they'll come up with a very thick, and then bid the job on that side, and then they can offer you some cost savings by you changing to something that's probably more realistic and more applicable for your applications. The good news is very few CIPP designs fail from design. The ones that I've been involved in on a litigation side is there's other factors that have caused the issues, but it's typically not a bad design. So the performance of these liners has been phenomenal and especially as we are careful on the design. So look at the existing hose pipe. If the existing hose pipe you're putting a liner in is in good shape, it's been carrying all those live loads. So the liner is not, you know, we don't have to get overly crazy on the live load on the liner design itself. If the pipe is in really bad shape and you're putting a liner in, then you maybe want to pay more attention because it will actually see some of those live loads.
Okay. Mark, there was also a couple questions in the chat. Great presentation, thank you. Outside of the 2-to-1, based on the Boston rule, is it fair to say live loads are negligible, or should further assessment be completed?
The Boston rule is used for foundation design. Again, it's approximation. It assumes that the stress is constant under the middle of the foundation and goes out to the edge. That's not really true. It's going to be much higher. So they AASHTO uses a tire stress distribution, I believe, of 1-to-1, and other ones use 2-to-1. So again, we have to make sure that we are doing those. How is it? I don't know the literature or any instrumentation to be able to say how well or which is the actual one. I wouldn't really matter. If I was a designer, I want to make sure that I follow a standard methodology and good practice in the industry. So if someone specifies as the AASHTO method, then I would use that distribution that they use. That way I'm protecting myself if there is a problem later on in court, because I can say, hey, I used that distribution on that side, which is the current standard or what was specified itself. Or if I use the CL truck, I would make sure that I use the distribution that's in the CSA standard itself. How do bends and fittings affect the stress distribution? Bends and fittings. It doesn't impact the stress distribution on the side. Again, what you can do is, depending on whether the truck is going at 90 degrees to the pipe, then it's the two wheels that cross over, the two axles that cross. If the pipe is running parallel to the truck, then you have to make sure that you're using the right axles, again, in the stress distribution on those sides. But again, we don't need to take in, again, do an FEA or anything unless you're very close to the surface and you had some unusual situation where you really want to do that. Then you may want to get into a finite element type of analysis on that side. I try to, so I think in 99% of the applications, we can use these conservative methods. If there's something that's going to give you a really high liner thickness and or you're really close to the surface, well, then you may want to be able to do that, but make sure you have someone that understands these live loads and the assumptions that are involved in it. Live loads may be negligible at 3+ meters depth. However, I think you should consider should be given for dead loads. Yeah, we still do the calculations for the dead loads, and we add the dead loads and the live loads on top of it. But soil arching is typically not considered in most liner designs because we're relatively at shallow depths. If you're at deeper depths, then you can start to get into soil arching. So again, there's another conservative component in the dead loads, which are the soil loads and the live loads. If you're less than 3 meters for a truckload, we would take the live load plus the dead loads and do the calculations. You got to remember, we're also designing for a 50-year design life, so we're predicting what the maximum loads would be in 50 years. But that's part of our liner design, and we do a course on CIPP liner design where we go through the live loads and the dead loads, and I have a calculator for that one as well, which I used for calculating. So so I'm not proponing we're only doing the design for live loads. It's live loads and dead loads that go into the CIPP calculations. I think the live loads and the groundwater loads and hydrostatic loads are relatively straightforward for most people. And the variation in design really comes from how much live load you're going to put on top of that as part of the application. So I hope I answered that question. It was a good question to clarify. Anything else, Caroline?
Yeah, I have one question. You sort of said between 1 and 2 meters, you need to be careful. If it's greater than 3, the live loads aren't as important. What about between 2 and 3?
Well, let's go. That's a good question. So I'm just going to go back and let's go look at the charts and then look at the distribution. If I can find it. Just hang on this. So these are truckloads. These are all Astro trucks, HS20, HS25. 25 is a heavier truck. HS30 is higher. So again, and these are typically either table values or ones that I calculate using my own calculator with the tire stress and the axle weights with respect to depths. Where there's gap, they're table values. So I can tell you this is a table value. The yellow one is an M55 flexible HS20 truck right here. So at 1 meter, this one says that the live load at 1 meter depth on that for that truck will be over 60 kPa. If I use one of these other trucks, so let's see if I can find a PPI one. A PPI one is here, and at 1 meter depth, it's going to say it's going to be somewhere below 40. That's almost a 20 kPa difference, which is going to have a huge impact on my liner thickness because I'm going to add another 20 kPa to the live load stress on those applications. When we get down to 3 meters depth, there's no difference between these different tables, right? So I'm going to choose somewhere around 10, 10 or 15. The percentage difference between these is relatively small. As we start to go from 2 meters and below, you start to see that the spread happens on these things. And theoretically, these things go off to infinity at the ground surface, which is not true in the real life. So they'll go to the maximum tire stress. So we'll take the stress, the load divided by the stress of the wheel. And that's what the maximum value will be from, say, 0.6 to here. So again, the spread really happens when we really get to 1 meter, and if we go below to 0.6, that spread even increases more, and that's where that variation comes from. So that's why I say pick a table value. These are both doing the same calculations for the same truck, but the table values are much different. So if anybody wants to see these table values, I've got them all handy. And if we teach a course, I'll go through exactly all these different table values and show how they are different. And then we can build a calculator to be able to show which one's right, which one do you want to lift by. But typically people will take the biggest one. That's why Ian Doherty and his calculator that's used around the globe, his spreadsheet calculator, he clearly specifies the table of values that he's chosen. And he doesn't allow you to do any calculations below a certain depth because he knows that this variation, and he doesn't want to get into, he said, contact somebody that knows what they're doing to be able to choose these loads. So he's built in his own conservative component on that part because he's recognized that as that variation. So it's this variation that we're looking for, and that's where the difference comes in your specifications. Does that help, Caroline? answer your question?
Yeah, I think so. I mean, I like between 2 and 3 year, there's not as much variation. And if you did a
Exactly.
sensitivity analysis, there's probably not going to be that much impact on your
No, but if
liner
you add
thickness.
but if you get into the train loads, railway loads in the CUIIC 80, which is not a real, then these values are going to go much higher, and they're going to go, and the spread's going to be quite a bit between those ones. So again, you're going to design a liner for something that's going to be way thicker than anything that will ever be applied. So then these are transport trucks. HS30 and HS25 are transport trucks, and most municipal cities aren't going to see transport trucks with these types of loads that are going to be applied to them, right? So again, these every year or every few years, they keep on putting a bigger and bigger truck. And the reason they're doing that, remember what these things are designed for and why they're specified is for highway bridge design. So it does make a big difference. These bigger, heavier trucks make a big difference in the amount of bending and shear that you're going to get into your bridge decks and your bridge design, which is a totally different problem.
Okay, thanks, Mark. There's just one last question. Well, I think last question, but it's in the Q&A. Will this presentation be shared? Any idea of when a full day course is planned for?
Full day course will probably be sometime in either the winter or spring of next year. In that time frame. If there's interest in doing it before, let me know. We can put it on. My fall is a little bit crazy, but I can definitely do it early in the new year if there's interest.
And I'm actually not sure. Do we share presentations?
I'm willing to share this presentation as a PDF. If anybody wants it, they can send me an email, and I will send it off to them if anybody has any questions. So my email is mark.knight@uwaterloo.ca. So it's right here. So feel free to contact me, and I can send you a PDF of this presentation and try to answer any questions anybody else has afterwards.
Okay, I just posted in the chat there. Okay, so I think with that, we'll sign off for today. Great questions. Thank you everyone for coming. And if you think about something later and you want to reach out to Mark, his email address is there, so feel free to do that. Yeah, thanks a lot, Mark.
Thank you.
This was great.
And, awesome. Thanks, everybody.
Looking forward to the next one. Check the CUIIC website.
Exactly. Get involved.
Yeah, it is. I'll just tell you, machine learning depiction of underground infrastructure by Peter, I'm not going to say his last name properly. Sarger. Anyway, looks exciting. That's October 13th. So check it out. And the next one is legal discussions, risks associated with underground construction, and then difficult ground conditions, trenchless contractors perspective, and that's Jean Woodbridge. That'll be great. And rural and Indigenous infrastructure challenges and development. So like I said, lots of good topics. Oh, thanks, Mark. So yeah, keep checking it out. Thanks for coming. I hope everyone, oh, hi, Peter, sorry. I'll be checking that one out. Peter's here. Okay.
And if anybody has ideas and they want this special topic, yes, please contact myself or Caroline, or send a message to CUIIC of something that you think is really needed. I know that we have a planning committee that is working on the winter for next year, and so give us your feedback and ideas.
Excellent. Thank you, everybody. Have a great afternoon.
Bye.
Thanks, Mark. Bye.